We are Moritz and Moritz, and we are going to tell you about how we built an open source, real-world end-user application in Clojure, and we're going to explain what that actually means for us in a second. But first, a few words about us. We are working in a software development services company based in Cologne, Germany, called Bewuta IT, and we have a strong focus in functional programming. And for example, the author of the chicken scheme compiler, Felix Winkelmann, is part of our team. And in the recent years, we've started adopting Clojure as our main go-to language. For example, we've also sponsored and supported the first German Clojure Bridge event just 2 weeks ago in Solingen. So if you want to find more about us and the services we offer, please visit our website. So when you look at Clojure conferences and the talks presented there, you often see either very technical and detailed talks like the one we just saw about data structure implementations, for example. You also tend to see people presenting their favorite library or the library they wrote. Also open source usually. You often hear people talk about enterprise experience reports, like, for example, the Daily Mail story we had in London, I think. So people putting Clojure to use for real-world applications, but usually behind bars, like in corporations. And often we are just that, right? So there's lots of philosophical idea and conceptual talk, programming language design, and all of that is very good, and this is actually the strong point of the Clojure community, I think, that we try to think about these details a lot. But when we submitted a talk for Euroclojure, or when we wanted to submit one, we thought about what is actually missing, what gap could we fill. And the gap we identified was putting all these things together, so essentially all the things I just mentioned. And then we remembered that we started this little project earlier that year, which is called Pepa, and that's what we call, as I said, a real-world application. So that's not just a to-do MVC toy example thing. It's like it actually does something and something useful. It's targeted at end users, so it's not like Riemann or something very technical where you already have to know about the concepts and details. It's actually focused at or targeted at office clerks who are supposed to work with that system. And it's actually an open source application as opposed to a library. So you can get your hands dirty with the code and you can look at it as a reference and see how we put all these ideas and libraries we always hear about to use. So we have actually built the whole thing with Clojure in the back end and ClojureScript in the front end. So this is what this talk is going to be about, basically. We're going to give you an introduction of how the code base works, so you can take a look at it when you're at home. You can have some reference points to go into. But first, let me explain to you a bit what Pepa actually does, so about the business domain, basically, which is just a short bit, and then we're going to go to the technical details about that. So Pepa is a document management system, and we built this product not for this presentation specifically, but because we had this problem. So we were actually scratching our own itch when we started this project. We were looking at lots of available open source document management systems because we needed one for the company, and our company runs like 95% in open source software. And the ones we took a look at, they didn't really fit with or didn't really fill our needs, and were designed horribly and slow, and you get the idea. So we thought, why not do it on our own? And the main issue you have, or the two issues we identified for document management systems are, on the one hand, how do you get documents into the system? So it has to have lots of input channels to make it convenient to input your documents somehow. And it has to be convenient because otherwise you end up with stacks of paper like that because nobody can be bothered to actually scan every document and upload it through a web form or something like that. So it has to be very, very easy and low barrier entry for documents. And none of the existing systems we looked at actually solved that very well. Another reason we didn't want to a commercial product, a cloud service, is because we want to have it on premise. So this is also something you could use on your own in your own servers. The second problem you have is once the documents are in there, you have to get them out again when you actually need them. So you file all your invoices, but then you have to do the tax report, so you have to have some efficient quick means to retrieve the documents again. So these are the two main problems. So this is what Pepa currently looks like. It's still a work in progress, so it's not like a released stable product or anything yet. It's out there, and development takes place in the public, and it's already pretty usable. So this is actually a screenshot I took the other day and of some demo documents, of course. And you can already identify a few basic ideas, like you have a search and a tagging system, pretty obvious, I think. And you can actually look at documents in the system, so you don't need a PDF viewer or anything, and it's all built into the web client, and it's using images for that. So this is what the interface looks like. But this is not going to be what we are going. This is not going to be a user introduction. This is going to be a developer introduction. So we are going to show you now how this system is built up, how the architecture works, and how we actually compose all these nice libraries we learn about in these conferences to build the system. So there's going to be a lot of code, be warned already, from now on. This is the last picture, I think. Oh no, there's another one. So this is a high-level overview of the system, or a graphical overview maybe. As you can see, we've chosen PostgreSQL as a data store, although Datomic, for example, would have been a very nice fit for our data model, because our document contents are immutable. So we never, once a document is in the system, you can't change its contents anymore. You're only allowed to change the metadata, which simplifies a lot of things about it. Many document management systems are like a mix of Google Drive or Google Docs and such a system. So you could actually call it more like a document archive system, maybe. So as you can see, this Postgres is our main data store. Then we have like lots of small components in this monolithic server, but these components are actually quite decoupled. We're going to take a look at that. So you could actually run them in separate processes eventually. That's what we're aiming for. It's not yet possible, but it will be soon. Then you have, in green here, you have multiple interfaces. As I said, you want to have various ways to put documents into the system. And we have this web client we just saw. We have an email interface, which you can also use from your scanner if it's capable to do that. And we have virtual printer interfaces. We're going to talk about that. And the blue components are like processors that actually do something with the documents you put in there to index them and OCR them and something like that. So that's the big picture. For actually implementing these components, we use the component library by Stuart. I think he presented it last year in Krakow, if I remember correctly. And so this is going to be our basis. I'm not going to explain the library itself now, just so you know where to look when you want to look it up. And that means that we have a central spot where this picture we just saw is actually manifested in code. So the Pepa core namespace contains this map, or this system declaration, and all the words we just saw in the diagram, you will find here as components again. So this is like your entry point when you want to navigate around the system, go to Pepa core, and from there you can easily find all the various parts of the system. So I'm going to start with a very simple example, the config component, which is necessary, like a boring necessity for every application. You have to configure it somehow to start it up, and so it knows where its services are. And that's something that's usually not mentioned in presentations about libraries, right? Because that's not the problem libraries have. So how did we do it in Pepa? Our config file is like this. So we use Clojure itself as a config language. Just put in a map like that with keys for the various components, and you have settings that you can put in there. And the component that loads that config is very straightforward. It looks like this. And the start method actually calls load file instead of read. Well, it doesn't just read the file, it actually loads it. So it works a bit like Emacs. At startup, it evaluates that file. So you can actually put code in your config file so you can read environment variables if you like and stuff like that. So all these things are possible in the config file. It's not restricted. And we do another trick here. We merge all the settings right into the component because the component is empty itself. We can just use it as the config, essentially. Right, so these configs are just records, and they are like maps, so we can use the component itself as a config object. So once we have the config in place, we can connect to, or we can talk to our database. And as I said, it's Postgres for open source reasons, basically, but also because Postgres has many, many features which are quite convenient and very mature, actually. And they're often a bit underused, I think. So we try to use lots of these features which are available in Postgres. But first, what do we store in there? We store metadata, obviously, but we also store the document contents themselves. So when you put a PDF in, it will be in Postgres too, because Postgres is actually quite good at handling large blobs like that. And then we don't have to fiddle with file systems and all the inconsistencies that arise from that. We just have transactional semantics for blob storage. We also use its full-text search capabilities, so we don't have to start up an Elasticsearch server or something like that. We could do that, of course, but it's very convenient because it's all built in. You just have one service, and you put all these functionality. You get all this for free. We also use it as a communication or as a message bus, you could say, device between components. So that is a way for us to later separate the various processes into separate system processes, actually. We're going to take a look at that in a minute. And we also use it as a persistent queue, or as a durable queue, because we have like these files that need to be processed, and there has to be some kind of queue so that the processors know what to process next. And we don't have a separate service for that, we just use Postgres too. So how does it? First, let's take a look at the schema, of course. That's what we need for understanding the whole thing. Focus on the middle vertical column. So you can see we have documents relation there, consisting of pages. And then there's also a files relation. So there's a split between documents and files, and that is for the reason that if you have a paper feed scanner, for example, you can just put your whole stack of mail on top. It will scan all the documents and put them all in a very big PDF. And then it can send it to Pepa. And in the Pepa web interface, you can then separate this physical file into logical documents. So you can tell it document A goes from page 1 to page 10, and the next document, blah, blah, blah. So you can separate physical files into logical documents, depending on the channel that you deliver it into it. So if you just upload a document, then it will be a one-to-one mapping. But the schema allows that. And the second thing you should focus on is this deletions relation, which is not really a business relation. It's just the fact that we can't know about deletions like we do in Datomic when somebody retracts a fact. There's a trace of that in the database, but in Postgres on relational databases, you just delete in place. So we have this separate relation that just keeps track of these deletions so that consumers can be notified about that. And the same is for changes in a table. So each table has a state sequence number that will just be increased whenever something changes in the table. When a new record is written or when an existing record is changed, then we can easily query for give me all the changes after that sequence number. We'll see that later in the front-end part. So this is the database component, very straightforward again. We just connect using our config component, and we use another trick here. We just put the connection pool object into a key called data source, which allows us to use the component itself as a JDBC connection spec. So we don't have to unwrap the component every time. We just use the component immediately. And this is going to look like that. So the PepaDB namespace is essentially a re-export of the JDBC, Clojure Java JDBC library, but it adds some features and wraps some things. And this is going to this slide here is to give you an idea how you can actually work on the system. Like when you set it up on your machine, how do you play with it? And when you get a REPL like that, you can just call the go function to start the system. So this is basically taken from the Stuart Sierra's component README. You start the system like that, and this will bind the system var to the running system. Then we can import the PepaDB namespace, and then we can run arbitrary queries on that using the DB component we just created. Right? So we can see there's some documents in there. We can also insert a new document, for example. And in the bottom, you see the state seek I was just talking about. So when an observer knew that the current state was 5, then it will just ask for give me everything after 5, and then it will receive this new document because it has state seek 6. But this is, of course, not how we actually implement the business logic. We have a separate namespace, Pepa model, that implements like the business domain in a more high-level way. For example, there's a query documents function that allows us to query documents using like a special DSL that we created for more convenient queries, because often we want to query for certain tags, for example, and doing that with all the joins is very involved. And then you want to query for tags which are there and not and stuff like that. So all these things are possible with this little DSL, which is actually our protocol for the front end. And in this case, we're searching for documents with a tag new, which have a title that starts with invoice, and that actually uses the Postgres full-text search. And we get this document metadata record, very shallow. We can add tags, for example, like that, foo and bar to a document of ID number 2. And then we can also retrieve a document, and that will give us an aggregate view of the current state of that document. And you can see there's like the associated objects are there too, like the pages, their processing status, the tags, and all the things. So you can work with this object more conveniently rather than working with a low-level database interface. So that's how that works. Now, when a new file enters the system, we have to somehow trigger this whole cascade of processing. And that's the heart of the system. That's why I'm going to go into details here now for a bit. This is a bit tricky. So we have a very straightforward store file function, which just inserts the file we want to store into the database, but then it calls this db notify function with a topic, basically. So files new is, it's announcing that it's inserted a new file to the database here. And the notify function you can see below, it does two things. First, it takes a transactional advisory log. That's a nice feature of Postgres that's pretty recent, actually, and it allows us to have logical logs. They don't actually log tables from inserts or anything. They're just advisory, as the name says. So when your application has to participate in this logging structure, and we use that to synchronize this transaction. So there's a transaction log that ends when the transaction ends, or is freed when the transaction ends. And at the same time, after that, we send the notification through this bus component. And the bus component is essentially a core.async publication channel, essentially. There's a bit more going on there, but that's what we do here. So we publish a core.async notification here, and on the other end, we have processors that listen for this notification. There are three processors, we already saw them. One that extracts pages and metadata from documents. So far, we only support PDF, and it's probably going to stay like that. Then there's another component that listens for these pages to be, which are created by the page extractor to render them into images. And then after that is the OCR processor, which extracts text from the image. Because sometimes you have PDFs that have images with text in them, right? So you have to do something like that. And this is what we use for the full text, as a basis for the full text search. And this is what a processor looks like. This is a bit tricky, or a bit much maybe for one slide, but bear with me. So we have this internal iProcessor protocol, which defines two things, or has to define two things. A query, how to obtain the next processable item from the database. So this is our queue we put on top of Postgres. It just returns the next pending object from the files table in this case. And we have a process item function that then receives that item if it's there and has to do something, can do whatever it like actually, but in that case it does the actual extraction, starting an external process for that. We use Poplar, and then after it's done, it also broadcasts such a notification via the bus, which is called, in this case, pages new, obviously. Right. So it's also this file page extractor is also a component. So we implement the lifecycle protocol. And in that protocol, we actually start that processor and we tell it what topic we are interested in. So whenever a file's new notification appears on the bus, we want to be called. That's what that says, actually. So let's take a look at this start function we just saw. Start at the bottom with the start function. We subscribe to the bus, so we get a notification channel. That's just a regular subscription channel from core.async, which is sliding, so we don't want to block somebody notifying us about something happening. We just want to get this information, so we use a sliding buffer here. We get a control channel so we can gracefully shut down this process, instantiate this processor object just for convenience, and then we start this worker thread. And it has to be a thread here because we start external processes and we have to wait for them, so we can't use a go loop. But that's fine. So and that thread just loops until it stops. And it processes the next item. So process next essentially, immediately calls next item, as you can see. And next item first takes this advisory log again, and that makes sure that once we receive the notification and we have taken that log, we know that the other transaction was committed. So this is just a synchronization point, so that we know we can actually retrieve the document from the database now. And then we fetch it from the database again. You might wonder, why don't we just send the whole document through the core.async channel? Because we already have it in hand. But obviously, we need a persistent queue anyway, and keeping all these documents in memory would be a waste, and it would also be stupid to block just because we have too many documents in the queue. We want to shove it right away, so that's why we do the round trip through the database. Right, and then we have, when we actually obtained an item, we process it, check whether there's something on the control channel to stop us, and if it's not, we just run into the loop again. If there was no item, we wait on this notification channel. So once the store file function is executed again, then we will be woken up here and continue with the loop for the next item to be processed. So in all these processors we saw, they are based on this component, or this implementation, basically. Well, this is the heart of the application. This is why I'm going into so much detail here, because that's something when you look into the code, you will have to understand what that does. Okay, and with that, I'm passing the buck to the other Moritz, I think.
Okay, yeah, that is easily the hardest part of the application, the most complicated code. So now we go to something simpler, logging. We have to do it, every bigger application, and it's a component-based application, so our logger is a component too. We abstract it away with a protocol, so it's pretty trivial. We define a log function, and it takes some arguments, a component, the log level, and the message. The bottom shows a Clojure tools logger implementation for it, also very trivial. But as it's a system-based application using components, we should be able to log on components. So that's how we want to use it. We just want to be able to call info and one and whatever on basically every component in our system. And so how can we do that? Either we implement the iLogger interface on every single component, which is pretty cumbersome and pulls state everywhere. We can explicitly define a dependency on a logger, which is also very annoying and easy to forget. So let's take a system as what it is. It's a map. Oh, sorry. It's a map. So we can just write some code which takes a completed system, the complete application, and adds logging to it, which will basically inject a logger into every single component. How we do that is with the wrap logging call. It takes a system and generates a logger with a namespace keyword, so there are no name clashes, etc. And adds an implicit dependency on every component and adds it. Pretty easy, but nice to have. The code is not so important in this case. It's just a strategy to add an implicit dependency to a whole system and make it available everywhere. Some things we have to be aware of. The logger has some dependencies itself, like config, and of course we can't add a logger to the config component itself, so there will be a cyclic dependency. So we just exclude that in the let all components above. But that's not so, it's actually pretty simple, but a very nice piece of code. And maybe it's useful for other people. As Moritz said earlier, how can we get data into this system? What can you do with a document on your computer? You can print it. So we implemented virtual network printers for the line printer daemon protocol and the internet printing protocol. LPD is pretty simple and pretty limited. IPP is complicated but very powerful. We have a more or less complete IPP implementation on our GitHub already, and IPP will follow soon. And those are tailored to Pepa, so it can basically just accept a document and pull the data out of it. Open source, blah, blah, blah. So basically, Pepa will appear as a virtual printer on your network. You can open your printing dialog on OS X or CUPS or Windows and print every document into it, and it's archived. The code for that is actually so simple, there's no need to show it. I would like to have to, but we don't have too much time. The HTTP API is basically very simple too. I won't show code either for that. It's just a mutant, the web server, We chose it for performance because Moritz tested all common web servers at the start. And later we saw that version 2.0 has really nice async support, which maps very nicely to our bus system and to core.async. That was just a very nice point we had there. We use Clojure for routing. I'm pretty sure most people will be familiar with that. And Liberator, Philip Meyer sits in the conference. I think he will enjoy that. Nothing special there either. So it's just the usual stuff. Transit is used, so we don't have to convert our data around to JSON and then back, as our client is written in Clojure script too. So just what you expect. The front end, as I said, it's Clojure script and Ohm. And the styling is garden. And routing is secretary. I will talk a bit about the data model we used for the client and a bit about the routing, because I think that's the most interesting part. And getting the data model right is usually the hardest part when writing a client. Oh yeah, and we used Freakwheel for the development process of the client. Yeah, it was really nice, really enjoyable. I can recommend it. So, the data model. Ohm recommends a single state atom for the whole application on the client in the web browser. I should say that. We have a mapping from document IDs to documents. We also do navigation, the routing itself of the client application in the app state. And we store the tags and the sequence numbers. As Moritz mentioned earlier, we use them to synchronize the client to the server. And basically, the server sends down a map with some sequence numbers for each table. The client just stores it, and when with the next HTTP requests, it sends them back to the server again, so the server knows if the client has the recent application state. And there is a long polling channel, which we use to pull changes from the server, and it waits 12 seconds or so and lets the HTTP request stay, and the server pushes data down as soon as it gets something. Also implemented with core.async and the bus channel, and the bus component, as Moritz mentioned earlier. Yeah, nothing so special here. A document in the app state is basically just exactly the same document as on the server. That's just what we got from get documents, pepa.model/documents, get documents. It has the title, the ID, all pages, and yeah. In the pages, the DPI key might be interesting. That's a set of the sizes in which we render it, the pages. So the client can decide for itself if it wants to show a low resolution picture of the page for thumbnails or a big resolution for full page view. Yeah, and if the render status isn't processed but failed or something, the client can show an error image or decide what to do. Yeah, that's the document. Routing is another interesting aspect. I saw some applications on GitHub which always call oms-root from their secretary handlers every time the route of the application changes, the URL, sorry. And I find that a bit cumbersome because every time the route changes, the whole application gets destroyed and reattached into the DOM, which doesn't map so nicely to the lifecycle in Ohm, which basically has a mount function which is called as soon as your UI gets mounted into the DOM, one that's called when it's removed, and one which is called when the state changes. And what we did here, we moved our queue and route right into the application state, and from our callbacks, which is called from secretary when a route matches, we changed that data. And yeah, that's basically it. So if the queue and route matches a document and some numerical ID, we just update our navigation ref, which is a ref cursor in the end, but we could also just call swap on the anthem of the application state and move and set the navigation data, which causes the application to get re-rendered. And in our root component, we just use core.match to match on that current navigation route. And if it's the dashboard, we just render the dashboard. If it's a document with an ID, we just render the document. And I think that's a quite nice solution on the routing issue in OHM, in the client. Okay, actually I'm way too fast, so I'm going back a bit and talk a bit about the database again. We see the render status key in the pages, which is basically a key if the status if the application already processed this page. It can be processed, it can be error, so in case there was a bad PDF or something, or if the render process just crashed. And it can also be pending, so the page isn't rendered yet. What's interesting in this here is that we have a namespace prefix keyword called processing status, which actually maps to a Postgres enumeration. So it's type safe when inserting it into the database. Many people don't use enumerations in Postgres and just use strings for their actual status, which is not type safe and might cause issues in so many cases, as you can just insert wrong data and do manual checks, which is annoying. And we wrote some JDBC code to actual map from namespace keywords to these enumerations in Postgres, which is very cool and makes it so much nicer to use. Okay. I don't have a slide for that, which is a bit unfortunate. Sorry. Not much I can say. Okay. Actually, I'm so fast. Moritz could talk longer. There's much more we can see. We have long polling implemented, as I said, which just keeps an HTTP request open to the server, and the server will respond as soon as something happens on the bus. We implemented SMTP, so as everyone knows, every application has to send or receive email. We can receive email, so you can just forward your latest invoice from your mail right to the SMTP server of Pepa, and it will render the attachments. We have zeroconf implemented as a component for announcing the printers, which is also pretty trivial, but makes it so much more useful, as the printer will just appear on OS X and in caps, and you can just print to it. I can talk a bit about the database schema and how we generate it. So at the start, we just wrote the SQL ourselves, which is the easiest part, but we can use all features of Postgres. As Moritz said, we really like to do as much as possible there, so we have it as easy as possible. But it gets rather cumbersome, as we have to add hooks to every table to update the state seek and checks and whatever. So in the end, we just wrote some code, a lining in task, which basically takes strings from the SQL and some metadata around that and generates the hooks accordingly. So we didn't use any SQL S-expression to SQL library, and because it wouldn't map to all the features we wanted to use. And we just kept it simple and wrote 5 functions or so to generate our schema. Yeah. We also have authentication and authorization, which isn't released yet. We have it in a branch. So I'm not sure if Moritz mentioned it. The whole application is work in progress. You can use it. We use it ourselves already, but it's not finished. Not even a bit. And so authentication and authorization is started. We just use friend for authentication and a pluggable protocol for authorization, so we can implement different strategies for different clients in the end, for different users. So we can implement a single user mode, which is just a HTTP basic auth. We can implement simple groups, and it's all plug-in based in the end. Okay, I think I'm done with that. Moritz? Moritz is...
So yeah. All these things are available on GitHub already, even the not yet quite released features, so you can take a look at the work in progress branches there too, at our repository. And we also welcome you to, I hope that this tour de force of the architecture and the code gave you like an idea where to start looking when you want to check it out. Maybe extend it or just use it as a reference when you want to build your own like real world application. You can maybe take some ideas out of that. And we license it at AGPL, so be aware of that when you submit pull requests, of course. And I think that's it. We still have some minutes, but first, thank you very much for your attention. I think we have